How a genius formula carved onto a bridge changed mathematical history. Robin Ariando of Conversation reports, on October 16, 1843, the Irish mathematician William Rowan Hamilton had an epiphany during a walk alongside Dublin's Royal Canal. He was so excited, he took out his penknife and carved his discovery right then and there on Broome Bridge. This is a picture of it right here. It's the most famous graffiti in the mathematical history, but it looks rather unassuming. I squared equals j squared equals k squared equals -1. Yet Hamilton's revelation changed the way mathematicians represent information, and this in turn made myriad technical applications simpler, from calculating forces when designing a bridge, an MRI machine, or a wind turbine, to programming search engines and orienting a rover on Mars. So what does this famous graffiti mean? Rotating objects? The mathematical problem Hamilton was trying to solve was how to represent the relationship between different directions in three-dimensional space. Direction is important in describing forces and velocities, but Hamilton was also interested in 3D rotations. Mathematicians already knew how to represent the position of an object with coordinates such as x, y, and z, but figuring out what happens to these coordinates when you rotate the object requires complicated spherical geometry. Hamilton wanted a simpler method. He was inspired by a remarkable way of representing two-dimensional rotations. The trick was to use what are called complex numbers, which have a real part and an imaginary part. The imaginary part is a multiple of the number I, the square root of -1, which is defined by the equation I squared equals -1. By the early 1800s, several mathematicians, including Jean R. Gand and John Warren, had discovered that a complex number can be represented by a point on a plane, and Warren had also shown it was mathematically quite simple to rotate a line through 90 degrees in this new complex plane, like turning a clock hand back from 12:15 p.m. to 12 noon. For this is what happens when you multiply a number by I. Hamilton was mightily impressed by this connection between complex numbers and geometry and set about trying to do it in 3 dimensions. He imagined a 3D complex plane with a second imaginary axis in the direction of the second imaginary number j, perpendicular to the other 2 axes. It took him many arduous months to realize that if he wanted to extend the 2D rotational wizardry of multiplication by I, he needed 4-dimensional complex numbers with a third imaginary number k. In this 4D mathematical space, the k-axis would be perpendicular to the other 3. Not only would k be defined by k squared equals -1, its definition also needed k equals ij equals negative ji. And pulling all these together gives I squared equals j squared equals k squared equals ijk equals -1. The revelation that hit Hamilton like a bolt of lightning at Broome Bridge. Hamilton called his 4D numbers quaternions, and he used them to calculate geometrical rotations in 3D space. It's kind of rotation used today to move a robot, say, or orient a satellite. But most of the practical magic comes into it when you consider just the imaginary part of the quaternion, and for this is what Hamilton named a vector. A vector encodes 2 kinds of information at once, most famously the magnitude and direction of the spatial quantity, such as force, velocity, or relative position. For instance, to represent an object's position, x, y, z, relative to the origin, the 0 point of the position axis, Hamilton visualized an arrow pointing from the origin of the object's location. The arrow represents the position vector xi plus yj plus zk. And the vector's components are numbered x, y, and z minus the distance the arrow extends along each of the three axes. Other vectors would have different components depending on their magnitudes and units. Half a century later, the eccentric English telegrapher Oliver Heaviside helped inaugurate modern vector analysis by replacing Hamilton's imaginary framework, IJK, with real unit vectors. But either way, the vector's components stay the same, and therefore the arrow and the basic rules for multiplying vectors remain the same as well. Hamilton defined two ways to multiplying vectors together. One produces a number, and the other produces a vector. And these multiplications crop up today in a multitude of applications, such as the formula for the electromagnetic force that underpins all our electronic devices. Unbeknownst to Hamilton, the French mathematician Oline Rodrigues had come up with a version of these products just 3 years earlier in his own work on rotations, but to call Rodrigues' multiplications the products of vectors is hindsight. It's Hamilton who linked the separate components onto a single quantity, the vector. Everyone else, from Isaac Newton to Rodrigues, had no concept of the single mathematical object unifying the components of a position or a force. Hamilton also developed a compact notion to make his equations concise and elegant. He used a Greek letter to denote the quaternion or vector, but today, following Heaviside, it is common to use a boldface Latin letter. And this compact notion changed the way mathematicians represent physical quantities in 3D space. With just a handful of symbols, we won't get into the physical meaning of all these. It shows how an electronic field vector spreads through space in response to change in a magnetic field vector. And there's a lot of formulas here you can see, all of these beautiful Latin and Greek letters. The power of perseverance. I chose one of Maxwell's equations as an example because the quirky Scott James Clerk Maxwell was the first major physicist to recognize the power of compact vector symbolism. Unfortunately, Hamilton did not live to see Maxwell's endorsement, but he never gave up his belief in his new way of representing physical quantities. Hamilton's perseverance in the face of mainstream rejection really moved me, and when I was researching my book on vectors, he hoped that one day, never mind when, he might be thanked for his discovery, but this was not vanity. It was excitement and the possible applications he envisaged. He would be over the moon that vectors are so widely used today and that they can represent digital as well as physical information, but he'd be especially pleased that in programming rotations, quaternions are still often the best choice, as NASA and computer graphics programmers know. In recognition of Hamilton's achievements, maths buffs retrace his famous walk every October 16 to celebrate Hamilton Day, but we all use the technological fruits of that unassuming graffiti every single day. And this is by Robin Arinaud, affiliate School of Mathematics, Monash University, on the conversation on Science Alert. Please leave your comments. Thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.